Good afternoon, this is Schweitzer, and these are the answers to our first lab test. All right, question number one says, grab a pen here. All right, it says we're doing our titration. Determine the moles of iron titrate in the sample. All right, so we have different trials here, and notice they're all same volume. They're all about the same level here. This one's a little bigger, so maybe we'll just pick one of them here. And I'm going to set up a little table here, which is going to be like this. Okay, this is not required, but this is some. We do this sometimes. All right, known, unknown. Then we have moles. Actually, I'm going to make this. Let's make this molarity, moles, and liters. All right, so it says here, determine the moles of iron in the sample. Well, again, here it's saying we're titrating against KMnO4. Here's the concentration of the KMnO4. So that's going to be the known item here. I'm going to go with 0.0196. All right, that's this guy right there. And then the volume used, I'll use the first trial. I'll use the middle one. Let's use 2023. 0.023. Make this a little thinner. All right, so 0.023. All right, and then on this volume here is going to be 50 milliliters, or move it over 3 spots. 1, 2, 3. That's 0.05. All right, that's much as dissolved in. We won't need that necessarily, but we're going to solve for our moles here. So in this case, molarity equals moles per liter. I'm solving for moles, so it's going to be 0.0196 times 0.023, and this gives me my moles. Calculator wise, I'm getting here 0.0196 times 0.023 equals 4.5 e to the negative fourth. And I'm going to do one more step here before I give an answer to this thing. I'm going to do dot line, get rid of the moles of MnO4 and go to the moles of iron. All right, and this is going to be jumping from here to here, or here to there, doesn't matter. 1 to 5 ratio. And then one more step yet. For every 1 mole of iron, I get out 55.8 grams. So 55.8 grams. Now this is going to give me my mass of iron in the sample. I'm going to give you this answer here as well, which will be the answer for this guy. So that value times 5 is going to be 0.0022. All right. So this is 0.002. I got 225. 25. Obviously, you know, variations are happening. All right. Now this number is going to give me my total mass. Take that thing times 55. And again, 55.8 would be fine. And you're going to get approximately 0.123. 0.123 grams. So to find this guy here, the percent mass is the mass of 0.123 divided by the total mass, which is 0.25 times 100 equals, all right, divide by 0.25, and I'm getting about, and then times 100 would be about 50%. Times 100, I'm getting a little under 49.5, but again, it's really close to 50%. So about, I'm going to put 49 0.5%, and you might get, I see other numbers here ranging everywhere to like 55%. So anything in that range would be acceptable. All right, so let's move along down here. It's unusual. All right. There we go. Perfect. Much better. All right. The last one here, again, this is a required question here, so all right, which of the following errors could have caused your percent error you circled in letter C? So they're saying that the unknown the known is said to have 12%. What's your percent error? All right, so let's do this. And I have 55% here. So my numbers got a little bit skewed here somehow when I did the little shift. So I'm going to answer this question here. All right, so I have 55%. I'm only supposed to have 12. So I want to do the difference between the two, all right, which is going to be 55. Okay, how you do it, if you 55 minus 12 or 12 minus 55, not a consequence to me at this point. I know my number's higher, my percent error is higher than it's supposed to be, so it's positive. It's lower, it's supposed to be negative, but absolute values are sometimes used, sometimes they're not. Either way, it just tells you the direction of error. Divide what you're supposed to have, which is 12, and then 55 minus 12. And I'm using the 55 or the 49, doesn't matter. 55 minus the 12 divided by the 12. Again, about 54% error. About 50% error. So we're having a 50% error listing here. Okay. Pretty much straight up. A couple different calculations kids I see, it's pretty close. 53, 54, somewhere around there. Okay, which a student titrated, so here this is probably one of the more challenging things here. Which of the following could have caused the error you calculated circle? Alright, so the student titrated past the equivalency point. Alright, so you want to kind of look at this and see what I'll move this back where it was. There we go. Wonderful. Alright, what was the error that happened? So if they titrated past the equivalency point, that's going to cause my volume of my known to go up. That's going to cause this to go up, causes the moles to go up, which causes the moles of iron to go up, which causes the mass right here to go up. And if that goes up, then my percent mass is going to be right here. This goes up, and then this goes up. So the answer is yes for the first one. That could cause my error. My error is that it's too big. All right. Sample of iron contained an inert impurity at the time of weighing. Okay. Now again, an inert impurity, this thing has lots of things in there that's not being accounted for. We're not just iron. The things that are in there that are inert aren't affecting our titration, and therefore will not affect it from the start to the end. No. Extra water was added to the iron sample for purposes of dissolving. Again, we're still going to have a certain number of moles of permanganate to match a certain number of moles of this guy. So we're saying this value here got larger. Doesn't matter. We're just using it for dissolving. No. Neither of these would cause any error, much less in the direction that we're looking for. All right, so that was our first calculation question. All right. These next ones should go a lot quicker. All right, which we titrate MnO4, which is strictly purple. Might say pink. It's fine. All right. Which is looking. Why are we also looking for color to reappear or stick around? What does this mean in layman's terms? What does it mean when the color remains? Okay, so essentially we have MnO4 negative, and when it goes to clear, which is Mn2 plus, means that essentially we have eliminated this. This is now our limiting reactant, and it just shows that the permanganate was used up. We standardize permanganate solution with oxalate ion. In terms of standardization, the term standardization means to determine or verify the solution's concentration for use in lab, other than the obvious reason for knowing concentration. Why is standardization needed? Some chemicals, as they sit around, could decompose, on a shelf. Some chemicals will pick up water. We call this hydroscopic. Yeah, so basically we want to make sure there was no change to the actual substance, that what you weigh it, that what you're measuring is actually what you have. Next one. A student is titrating until the reaction turns pink, purple, and ends up titrating way too long. How would this numerically affect the answer? Explain with cascading math. Again, that would be the volume of the MnO4 is going to be too large. Therefore, the moles is too large. And therefore, the moles of Fe is too large. Makes the mass of Fe too large. And therefore, the percent mass is too large. Go over there. All right, next page apparently. Yes. All right. Hydrogen peroxide is decomposed by this following chemical equation. All right. 10 grams of this 3% hydrogen peroxide is decomposed at STP. Answer the following questions. The vapor pressure of water is 23.8. The total pressure of the container is 1 atmosphere after gas is collected. What is the total partial pressure of this guy? Okay, so here we're looking at 1 atmosphere, or let's go 760 is my standard pressure. You can go 1 if you'd like. Minus the 23.8, which is the vapor pressure, will give us our next calculation. 760 minus 23.8 is 736. Now this is in millimeters of mercury, or torr of Hg, or it's like 0.96 atmospheres. You'd want to show work if you did any work there. What is the total mass of H2O2 present in the solution? Okay, so in this case, to do this, we have 10 grams at 3% by mass. Okay, so letter B is going to be pretty simple. 10 grams times 0.03, and this means 3% of the 10 grams. 10 times 0.03 is 0.3 grams. All right, what would be the volume of the hydrogen oxygen produced? Show work below. Okay, so we're going to do this closely. All right, so we got, in this case, 0.3 grams, dot line, get rid of grams and go to moles. This is the hydrogen peroxide, H2O2, 1 mole. Okay, H2O2, this is going to be 2 plus 32, and that's 34 grams. And then dot line, for every 2 of these I get 1 oxygen. Okay, so at 2 to 1 ratio, this gives me moles of oxygen. Calculate that quickly. So 0.3 divided by 34 divided by 2 is 0.0044. Alright, 0.004411 moles of O2. And then I'm going to probably just use Pivener at this point, or because we're STP, well, it says we're STP, but this is not the pressure of just that guy. So we're not STP anymore. All right, so I'm going to do this here. PV equals nRT. I'm looking for volume equals, okay, so moles 0.0044 times R. I'm going to be in, let's go in atmosphere, so I'm going to go 0.0821, and then the temperature is 200 and, well, it's saying STP, so 273 technically, if we're close to freezing. And then this would be pressure 0.96. All right, calculate that. It won't be much different if you don't use the dry vapor pressure. 0.0044 times 0.0821 times 273 divided by 0.96 equals 0.102, okay, 0.102 liters, and that is my volume of just the oxygen gas. All right, what's the purpose of the iron ions? This is a catalyst. All right, what else we got here? All right, iron was used in the reaction was iron, was orange and yellow. Then why do we not see that color disappear over the reaction? Because a catalyst, okay, is not consumed, or a catalyst doesn't wear out, so it is always there at the beginning, it's always there in the end, not consumed. A student runs this experiment and some water spills in and is not recorded. How will the effect of this error cause an outcome of H2O2? Well, in this case, be specific on the error. Okay, so the student runs this experiment and some water spills and is not. Okay, so this is after they're recording it. Okay, so you collect your water, and that means that my molarity of this thing is equal to moles per liter. Okay, they're saying I spilled some of this. My error is that this is smaller than it should be. That's the volume. So the water we collected is equal to the volume of the gas. So PV equals nRT. Actually, I want to take that back. This volume is not affected. This is the amount of the volume of H2O2 that we actually measured to begin with. That's not what they're referring to. I probably should be a little clearer in this, but they're referring to this volume right here. So the moles is equal to the PV over RT. So if the error is that this volume is too small, and if this volume is too small, that's going to drive the moles down. If the moles goes down, then of course the molarity goes down, and that's my answer. All right, last lap. 2.5 gram copper strip of iodine is heated and the reaction takes place. After the reaction took place, it was 2.59. It was cleaned off, and it's 2.45. All right, what is the empirical formula given the data show all work? All right, so we're going to take this guy minus this guy, and that's the amount of iodine we're going to get. So this is going to be subtracting those two, 0.09 grams of iodine. Okay, and then the copper reacted is going to be this guy, would be this one minus this one. So we're talking 0.05. 0.05. All right, dot line, get rid of grams and go to moles. Dot line, get rid of grams and go to moles. All right. Grab a periodic table. Molecular weight for iodine is going to be 126.9. All right, so we got 126.9 26.9 to 1. All right, and then this one here is 1 mole of copper is equivalent to 63.5. All right, so we'll put that in here, 63.5. We're going to divide out, and we will get 0.09 divided by 0.09 divided by 124.9. Can't read my own writing there. Iodine is 126.9. I'm getting on this guy 7.09 e to the negative fourth. 0.05 divided by the molar mass of copper, which is 63.5, 63.5, and I'm getting 7.8 e to the negative fourth. You might see a relationship forming here. It looks like they're pretty close to 1 to 1. And if you divide by the smallest one, you're going to get pretty close to a 1 to 1 ratio. So my formula is Cu I based on that data. What color is iodine vapor? It's purple, or something like purple. You have many strips that were not fully cleaned. All right, copper iodine mixture. How would this affect the air of the empirical? How would it affect the empirical formula? This is an air. Your job is to explain how it will affect the air. So we only have we have 3 weighings here. So we want, how we can figure this out is, how does the air, which massing does it affect? So it says I have seen many strips that are not fully cleaned of copper iodide mixture. How would this affect it? So again, I guess we'll say that the last one is not fully cleaned. So when you went not fully cleaned off, this thing, the error is that this mass is actually higher than it's supposed to be. So this thing should, error is that this is higher. That's the error. So this is going to affect, because it's the third one, it's only affecting the copper. So copper initial weighing minus the copper on the third weighing, and I always follow the error. Okay, the error is that this is too big. Right? It should be smaller. It's too big because it isn't cleaned high enough. Some of it was removed. So this is going to cause this value to seem too small. And if this is too small, then the mass of copper is going to be too small. And of course, the moles of copper will be too small. And this makes my ratio of copper seem smaller, and my ratio of iodine, therefore, seeming larger. So it could, that's the result right there. A student working very hard overcleans the strip, okay, making the overcleans the strip prior to the last massing, causing lots of copper to remove. This is just the opposite. I'm taking copper initial that wasn't affected minus the copper, okay, in the third weighing. This is going to be small. The error is smaller than it's supposed to be. All right. Now we subtract that value. That makes this thing larger. And I'm not going to go ahead with all of the same analogies, but essentially it reverses the process, makes the copper seem larger than it's supposed to be, and consequently the iodine could be therefore smaller than it's supposed to be. And that is the end of our particular quiz, our first lab quiz. Thank you very much.